Okay, so question 1, what is happening here? In the circuit figure, that's figure 1.1, calculate V0, I0 when Vs is this in part 1. In part 2, they want us to find the same thing when Vs is 10 volts. So this is the basic question really, and they just want us to basically just use the same concepts of circuit analysis, and this is very, very basic. Let's see what you have to do here. So there are various methods that you can use to get I0 or V0 here. V0, by the way, it's the voltage across this 1 ohm resistor. So whatever the voltage the 1 ohm resistor is using, that is V0. And then I0, on the other hand, is the current that comes to pass through the 1 ohm resistor. So for this 1 ohm resistor, when we use Ohm's law, V is equals to IR. So for that 1 ohm resistor, the voltage is V0, which is the voltage used by that 1 ohm resistor. The current passing there is I0, and then the resistance there is 1 ohm. So this is Ohm's law for the 1 ohm resistor there. Now, how do we find I0 and V0? There are various methods we can use. We can use Kirchhoff's methods, that's the current law and the voltage law, by looping around. We can also use mesh analysis to get the mesh current through the 1 ohm resistor, and then from there you can get the other. Notice that all you need is either to find V0. If you get V0, you can get I0, or find I0. Once you have I0, use it here, you'll get V0. So you just need one of them. So whichever method you're comfortable with. Or since I am not seeing any other source being present here, we only have one source, which is Vs. We see that here we can just use the old school method of rewriting this circuit, getting the total resistance in our circuit, and then get the current that will be coming from the source. See how it will split until when you reach the very end. Even that can be utilized here. So I will allow you to choose which method. Pardon?
Thevenin, whatever, it can't work.
Which one? Thevenin?
Thevenin, I don't Thevenin.
It can.
That one.
It can work. You prefer that one?
Yeah, because you haven't done enough practice on that one. Or if you did, maybe you did it to the boys.
Okay. So we use Thevenin here?
Yeah.
Great. Okay, Thevenin is one of those special methods which are used to analyze circuits, and this is going to be a good example on that method. So I'm glad you suggested that. I was going to pick a lazy way of doing it. I'm saying lazy because Thevenin mostly is utilized to simplify complex circuits. Okay, so for this one, we can solve it using easier methods, but for practice, yes, we can use Thevenin. And what you can actually try is, try to see if you can find the same answers by using other methods as well. Since logically speaking, regardless of the method you use, you should find the same results. Okay, so all the resistors here are 1 ohm. Okay, in Thevenin's method of analyzing circuits, first understand the section you're trying to analyze. In this case, we're trying to analyze what is happening to that branch. So whatever that is, that becomes our load resistor. In the first case, of course, Vs is 1, so we'll keep that in mind. Okay, so in the first case, sorry, not that. Okay, so for this case, Vs is equals to 1 volt. So in Thevenin's method, what do we need? So first, understand which one is your load. So the load resistor will be the resistor we are analyzing, which is the 1 ohm resistor. But since all these are 1 ohm resistors, we'll highlight this to be the load resistor here. Okay, so once you have highlighted or seen which one is your load resistor, in Thevenin's method, the first step is to open the load resistor. First, let me start with a preamble on what you need. The goal of Thevenin's theorem is to reduce the circuit so that it reduces to a Thevenin's equivalent circuit. A Thevenin's equivalent circuit will only have a Thevenin's equivalent voltage, V Thevenin, connected in series with a Thevenin's equivalent resistance, R Thevenin, and then this is connected to the load resistor. So this is the Thevenin's equivalent circuit. So the goal of Thevenin's equivalent circuit concept is to find what will become the Thevenin's equivalent resistance so that we can put it here, and then find what will become the Thevenin's equivalent voltage and put it here. The logic being, when you reduce it to a circuit like this one, finding what is happening to RL becomes easy, because for this circuit, the current is the same. So if we label the current as just I0, we see that we can easily say that we can now use any method here, minus V Thevenin by Kirchhoff's voltage law, and then we'll have plus I0 multiplying R Thevenin plus I0 multiplying R load. So I'm just adding the voltage here plus the voltage here plus the voltage here using Kirchhoff's voltage law. So by finding what R Thevenin is, since we already know the load, this of course is equals to 0. Notice that we can easily get I0 as it will be equal to just V Thevenin this side. And then finally, the load current, I naught, will be equals to V Thevenin divided by R Thevenin plus R load. So if we can find R Thevenin and V Thevenin, notice that it becomes easy to get what I0 is. And once we have I0, remember we already saw to say that V0 will just be equals to I0 multiplying the load resistor in this case. So if we can find what R Thevenin is and V Thevenin is, then it'll be good. Now that we know how Thevenin's method works, how do we find R Thevenin and V Thevenin? Well, for this circuit, it's a little bit straightforward. So this is what we have. So what happens here? In step 1, open the load resistor. So here, of course, if you are opening the load resistor, then it means that you're trying to find V Thevenin, which is the open circuit voltage. But if you find that to be a little bit difficult to find, you can still use an alternative approach, which is to find the Norton's current or the open circuit current. Not the open circuit current, sorry, the short circuit current. That is one way you can look at it. So now I'm trying to analyze. If I open this, if I remove this, if I remove that point, will it be easy for me to know the voltage difference between this point and this point? I think it will. So step 1, we're going to open the load resistor. So by opening, of course, just remove it from the circuit. So we've removed that 1 ohm resistor. Now, once it has been removed, find the open circuit voltage. So it's basically the voltage that was going to connect where the load resistor was. That open circuit voltage, so open circuit, will be the one that will be equivalent to the V Thevenin. But how do we find that voltage? You see, when you look at the circuit the way it is, it might not be clear how you proceed from there. But let me redraw the circuit so that you see how it becomes. So this circuit, when redrawn, I'll start from the power source. Here, you have the voltage source, Vs. Going up, you come to this node here. From this node, I am seeing you go to the 1 ohm here, this 1 ohm. From the same node, you go up. And then I'm seeing you find that 1 ohm there. And then I'm seeing a continuation. As long as this line is not there, I'm seeing that from this 1 ohm, you still come to pass through this point, through that 1 ohm, the other 1 ohm. So from this one, it's like we come down. Where am I going to put it? Let me put it the other side. I pass through the second 1 ohm there. This 1 ohm here, that is this one here. And then this point here, I'll label it as my point A, and this is my point B. Okay, I've drawn the upper part. Now we have this bottom part. Okay, so if I put this one here, notice that I am just going back to the same circuit the way it was. I haven't really changed it much. And it's still workable from here. This is still fine. But I always feel like there is a way that we can present this so that it's a little bit more straightforward for you to see. Node A is somewhere down here. Node B, I mean, is somewhere down here. All I know is that between this 1 ohm and this 1 ohm, there is that node. So I can still rewrite this part. I'll move this one out for now, so that now, and I didn't have to move that, I can keep it here. I'll just put the second 1 ohm here so that it is right here. Okay, so again, this one is this one. From it, we pass through A to find the second 1 ohm here. So from this, we pass through A. A is somewhere between, so I'll put A there. And then we reach the second one here. All we should have is, from this one here, where should we go? From that one, we should come through this and this. Do we have that? Yes, from this one, we go through that and that. So this is better. I always feel like presenting this question in this way makes it easy to analyze. So this is point A, then point B is down here. Again, you could have still worked it out from this one here, but just for presentation, I have redrawn it so that it looks like this. And you must understand to say that the two circuits are the same. If you understand that, it becomes easy for you to analyze the circuit. Okay, so how do we find the voltage VA here? So again, there are still various methods that you can choose to use here. Among the methods, you can choose to use nodal analysis. Do I want nodal analysis? Yeah, we can choose to use nodal analysis here. So we can choose to use nodal analysis if we want, or we can just understand one thing. This, whatever is here, firstly, these two are in series. These two are in series. So since those two are in series, they can easily be added to get a 2 ohm. And then once you get that 2 ohm, let's transform it. Once you get that 2 ohm, somehow I always try to find the easiest way to work it out. Nodal analysis works here, but this method of just transforming this to a skeleton's form, it's what I think you learn first in high school, which I feel becomes easy to relate to. So this 1 ohm here is this one here. The 2, for now I have swallowed A, so A is not showing up. So for now we have swallowed A there. So the 2, when these two are combined, when you get 2 ohms there, and then you come to this 1 ohm here. Okay, so in this state now, what is happening? Okay, so these two are parallel. Being parallel, we can easily add them up. So what I want to first get, I'm trying to see if maybe node analysis is better here to get the node voltages. I might resort to node analysis in the end. Here, there, here and there. Okay, let me just go with node analysis. I think it's smarter. This is lazy, but might require me to do a lot of things. Okay, so if we're using nodal analysis, what do we do? First, pick a ground it at that point. So I'll pick this line to be the ground. If this line is my ground, notice that B, that is where B is. So it implies that VB becomes equals to 0 since that is my ground. Now we want to find VA. And then the voltage difference between A and B, which is our V Thevenin, will be equals to VA minus VB. But since VB is 0, in other words, V Thevenin will basically be the same as VA. So this is what we're going to result to. So how do we find VA? To find VA, stepwise, I'll assign certain nodes. So I'll get this node. I'll say this is VC, and I'll put this as VD. Those are some of the nodes which are important here. So how do we find that? Here you only have a voltage source. On one end you have the ground, 0 volts. The other end you have VC. So we see that at the positive most end you have VC, negative most end you have a 0. This is equals to whatever the voltage is supplying, Vs. So in other words, Vc is the same as Vs. So whatever is here, this will be the same as the Vs. In the first part, Vs is 1 ohm, 1 volt, sorry. So there, I might as well put Vs. Once you have that, we can now go to VA here. It's kind of primitive. I'm just putting it there because I want to know exactly what it is, so we use it still. So if I come to this one here, what is happening? We'll assume current is coming this way, going in that direction, meaning that here it is going this way, here it is going downwards. So again, in nodal analysis, what you're going to use is going to be Kirchhoff's current law or the junction law. So at the highlighted junctions, I'll be summing currents that are entering there. But you have to remember that from Ohm's law, V is equals to I R. This implies that I can be written in terms of voltage over R. But the voltage that is here, it is the potential difference across a line. So if I have a component like this one with resistance R and the current I passing in it, I can find the voltage it is using by comparing the voltage it was fed, V1, and the voltage that left it, V2. So I can now say, since in Ohm's law, this is V over R, this voltage drop across that resistor will be equal to the voltage it was fed, V1, minus the voltage that left it. Why are you writing R? The voltage that left it, V2, over the resistance of the component. So this is going to be how we're going to get the currents. Again, this is just to remind you. I think we should have discussed this when we did the current, not current law, when we did, yeah, I think it was the current law. We should have done this. Okay, so with a reminder in place, let's add the currents now. So for this node, the node labeled A, what is happening there? You're going to have current entering through this 1 ohm resistor. To get that current, remember I can assign them I1, 2, and so on, but we can just quickly jump through to express currents in terms of voltage and resistance. The voltage being fed to the 1 ohm is Vs. So it's being fed Vs. The voltage leaving the 1 ohm resistor is the voltage at this node A. So minus Va over the resistance there, which is just 1. This is an expression to tell us the current passing through that 1 ohm there. Then, in terms of the node, notice that the current here will be entering the node A. Because it is entering, we'll assign it a positive. This expression will be positive. Remember, entering will be positive, leaving will be negative. Minus, to this 1 ohm now, current here will be going downwards. Entering it, Va, the voltage entering, leaving Vd. The resistance there, 1 ohm. So this is everything for the node at A there. So this has to be equals to 0. From this, we see that Vs minus Va minus Va minus Vd must be equals to 0. So that here, Vs minus Va minus Va plus Vd must be equals to 0. Now we have Vs minus 2Va plus Vd is equals to 0. So notice that the method we are using to solve this one, it's similar to what we use in part 2. The only thing that will change in part 2 is our value for Vs. So I'll keep this as equation 1 so that when it comes to part 2, we'll only be changing what Vs is. So if Vs is equals to 1 volt, notice that now we're going to have 1 minus 2Va plus Vd is equals to 0. From here, we see that, we can leave it here, or we can take everything else to the right, except 1, we'll have 2Va minus Vd is equals to 1. So this is what we have. Okay, now having done that, let's go to the other nodes. So now the only other node remaining here is the node where you have Vd there. So at this point, what is happening? You have current entering from here. Remember, the current entering from there will be Va minus Vd over 1 ohm. Basically the same expression we came up with for that 1 ohm resistor. Then here current is also entering. So this is going to be plus the voltage it was supplied, Vs, minus the voltage that left that, Vd, divided by 1. Then lastly, you have this 1 ohm resistor where now current is leaving. So that one is going to be minus. Minus the voltage it was fed, Vd, minus the voltage that left it. It's going to the ground, V0. I can say Vb, but it's ground voltage, so that's V0 over 1 is equals to 0. From here, Va minus Vd plus Vs minus Vd minus Vd minus V0. V0, that's just a 0. So I might as well just put this as a 0. And then this would reduce to this. Now, VA, these will add up. So you're going to have minus VD minus VD again, then minus VD again, then plus VS is equals to 0. This is now VA minus 3VD is equals to 0. So I'll keep this as equation 3 because when it comes to question 2, I just want to come and change what VS is. If VS is equals to 1, the expression becomes VA minus 3VD plus 1 is equals to 0. Now, just by coming up with this second equation, number 4, notice that I can now solve number 2 and number 4 simultaneously because they all just have VA and VD. So I can make VD subject in one of these equations. So let me make VD subject here. VD will be equal to, I already done that. VD will go to the right, 1 will come to the left. That is what VD is. So I'll get that and put it where there's VD. So VD is equals to 2VA minus 1. So that from here, then finally, then we have VA is equal to, goes there, this will be 4 over 5 volts. Since we have VA, remember earlier I did point out to say that V Thevenin will be the difference between VA and VB. Not the other way around. It has to be VA minus VB. VB was the ground voltage after using nodal analysis, so it's 0. So VA will be 4 over 5 volts. So this becomes our Thevenin's equivalent voltage. Okay, so having found that, for our circuit, we have now found V Thevenin. Notice that we can still use the same methods for the second problem in part 2, where they want us to find when Vs is equals to 10. We'll still use the same approach, but here we'll now use Vs is equals to 10. Everything else will be the same. Equation 2 will change, of course. Now it will be a 10 this side. This will now be a 10 there, minus 10 there. And then once you get that minus 10, you come and substitute it here. This will be 2VA minus 10. When solving, what else will change? When multiplying by 3, this will still be 6VA, but this will now be 3 by 10 to be 30 there. So now this will be VA minus 6VA plus 30 plus 1 is equals to 0. This will be minus 5VA plus 31 is equals to 0. VA will be equals to 31 over 5. So of course you can do it stepwise to just make sure that it is indeed coming out to be this. Okay, so we have now found V Thevenin. So after finding V Thevenin, in the next step, you now want to find R Thevenin. This is using Thevenin's method. Now, to find R Thevenin, what do you do? Well, in this approach, when you're finding R Thevenin, you now go, you can even get this one here, the one without the load. So I've gotten the same circuit without the load resistor. Let me complete that. But what are we doing this time around? To find our Thevenin, what we're going to do is we want to do two things. If your circuit has got a voltage source, an independent voltage source, you're going to short it. So short or independent voltage sources. If your circuit contains current sources as well, current sources must be opened. Here in our circuit, we only have one source, and that's a voltage source. According to that instruction, we're going to short it. So in place of the source, we'll connect it with just a short circuit, which is a wire like that. Once we have done that, you now want to find the equivalent resistance viewed from the points where the load was connected. So this is what we're going to do. It looks weird when you look at it like this. So to make it more clear what you have to do, look at point A as if it was a node like this. It makes it more clear that you're finding the total resistance viewed from here. Meaning everything else here must be connected, must be presented as one thing. So how do we do that? How do we find the total resistance? So here, of course, you just have to find a way of looking at this circuit in a better way. So let me try to redraw it. Hopefully it becomes simpler. If I can avoid using the transformations, delta transformations, I'll avoid them. So let's see if it is possible. Be very careful. There is this line that does not have anything now. That is a short circuit. When you have a short circuit, it actually means that this point and this point are one and the same thing. What does that imply? This 1 ohm here, I might as well just say it is here, put it here, and connect it here. Whether I connect it here, connect it there, same thing. Even this 1 ohm on top, I might as well just bring it and connect it here. And then after doing that, remove this unnecessary line since it's basically not doing anything. So this is still the same circuit. Do you follow? Okay. You see, by redrawing it, if you compare the two circuits, this is the original one, the one we had before I observed that that is a short circuit now. This was the original one, of course, without the source. Notice that here, it might have been a little bit difficult for you to see things, but look at the way it is now, after observing that this point and this point are the same. It now makes sense, or it is now clear for us to see that the 1 ohm and the 1 ohm there are actually parallel to each other, those two. If they are parallel to each other, we can actually transform them. Since you have a 1 and a 1 parallel to each other, their combination will be equal to, if you're combining 1 and 1, just multiply 1 times 1 over 1 plus 1. We see that this will be 1 over 2, 0.5 ohms. So in place of these two, I can now just write my circuit so that they appear as one resistor. So in place of these two, I'll now just place one resistor. But look at that. Now it looks more obvious. Do you see that these two are also, these are in series, right? That's clear, right? Since those two are in series, we can actually just add them. Their combination will now just be 1 plus 0.5. So this will be equals to 1.5 ohms. So now our circuit changes once more. When you're doing it in the exam, of course, you might not want to keep redrawing because that will waste a lot of time. But if you can, it's always better and easy to follow. But you don't have to show all these diagrams, some are necessary. So these two are combining now. But notice that I'm still connecting them to the same points. This is now 1.5 ohms. Then look at that. Now the 1.5 and that other one, these are now in parallel. So that the overall connection now, which is the equivalent resistance, since now I've combined everything, the total resistance, which is our Thevenin, I need to multiply the 1 and the 1.5 over the same, but now added. So this will be 1.5 over 2.5. Okay, so we get 0.6 ohms. So now we have R Thevenin, and earlier we found V Thevenin. So our R Thevenin 0.6 ohms, our V Thevenin somewhere here. We got, what was our V Thevenin? V Thevenin was 4 over 5. And then our load comes here. So with these figured out, we can now easily get the current coming through this, which is I0. And then we can also get the voltage across this, which is V0. We already did the formulas for this, so we can just use them so we don't have to go through those again. So these are the formulas we're going to use for I0 and V0. Okay, so for I0, V0 is 4 over 5. Our Thevenin 0.6, our load 1. So what are we getting here? So we get 0.5 amps. Now V0. V0 will just be I0 multiplying our load. I0 we just found 0.5. R is 1 ohm. So this is 0.5 volts now. So we have just obtained I0 and V0 for our circuit. Another method that perhaps could have seemed a little bit shorter to work out a problem like this one, it's just get the total resistance. Of course, it might not be as short, but at least to do one method. Get the total resistance of everything here. To get the total resistance the way it is, you might want to use star to delta transformation here. Once you use star to delta transformation here, you'll be able to finally get the total resistance for everything. Once you get the total resistance, find a way of getting the current that comes here, current that goes there, current that comes here. You don't even need to worry about the current that will go there. As long as you know the current that is coming this side, you see these two combine at this point to give you what I0 is. So if you can find the current that is coming this side and the current that is going this side, added together, they'll give you I0. Once you have I0 multiplied with 1 ohm, you get V0, then you're done. So this is another method that you could have used to obtain I0. Other than that, you could have also used mesh analysis. Loop here, and loop here. Mesh analysis or Kirchhoff's voltage law. Those two methods could have also worked here to give you I0. The best thing about those is you could have just been stuck with just one method, which is better. But with the Thevenin method we selected, we at some point had to resort to using nodal analysis. But as long as it works, I hope it helped. Okay, that's all.